All right, so today I want to explain a very interesting idea. The idea is that we want to use mutual information for semantic hashing, and it is done by many researchers, such as Fatih Gacir. For example, one paper is hashing with mutual information from Boston University, and they use supervised hashing based on optimizing mutual information. And they use mini-batch stochastic gradient descent. In object detection or text summarization, we want to reduce dimensionality of data to allow for efficient retrieval of similar instances in large databases. Remember my lectures about information retrieval? It's really hard to get some relevant data, so we need some mechanism, and semantic hashing could be seen as one of them. So when there is an available supervision, there are class labels, everything is easy, and you have seen how you can use also triplets and those things. And now I want to talk about a parameter-free method, unlike other previous methods based on ranking or other methods. But now this time, there are no parameters, just like non-parametric Bayesian. So the goal is learn hashing functions that can result in optimal nearest neighbor retrieval performance. That supervision can also be given in terms of local relative distance comparisons. Like, as I said, triplets, where one example is constrained to have a smaller distance to the second example than the third one. So this is called local ranking, and you know that. You have seen my previous lectures. But loss functions in local ranking methods are usually only indirectly related to retrieval performance. So we need additional regularization terms. You know the importance of regularization in machine learning as well. So good binary embedding should well separate neighbors and non-neighbors. Neighbors, for example, we have a node, we have some neighbors. But the red dots, the red nodes are just non-neighbors. So these belong to theta, belongs to minus, and these are neighbors, so they belong to plus, positive elements. So good binary embedding should well separate neighbors and non-neighbors in the Hamming distance. Low neighborhood, and that is what we call low neighborhood ambiguity. It is quantified by mutual information, and as I said, the pros are things like it is parameter free, it's scalable, and so on. To optimize mutual information, we relax the original NP-hard discrete optimization problem. And I will explain what I mean. Data-dependent binary hash methods are binary embeddings that map the data into Hamming space. Remember data-independent things like locality sensitive hashing, LSH, that I have described in my playlist in metric embedding. Those things are not useful because they don't respect the data distribution. They implicitly preserve some distances, but they don't care about your data distribution. So, and also some people have, I think Ilya Ilya was one of them, wrote a very interesting article in 2015 saying that, all of these data dependent methods are much more, are much better. They're much faster, much better, more scalable than. They can represent much better than data independent methods like LSH. So LSH is not good. That's why the new research is about data dependent method, because they respected your data distribution. So data dependent methods are binary embeddings that map the data into Hamming distance, and they simultaneously preserve a specific neighborhood structure. Such a neighborhood structure can be derived from labels or by similarity indicators of data pairs. So hashing. So what is hashing with mutual information? So let X be a subset of Rn, be your feature space, and HB is just -1, 1B is just B-dimensional Hamming space. And the goal is finding an embedding, we want phi, an embedding from X to our beautiful B-dimensional Hamming distance HB, such that it induces a Hamming distance d phi, which is the number of bits differences between embedded vectors. For example, if you know coding theory, error correcting codes, we want the distances between them to be big. But now that we have a different concern. Those concerns are for different purposes. Those because the channel is noisy, the communication channels. Because I was an electrical engineer, we used to care about how we can encode and decode so that the noise doesn't affect our transmission of information, and those error correcting codes were particularly important in order to do communication. But now we have a different concern. So the distance that is induced is, from any point, any pair, distance is just one of these things up to B, because it's a B-dimensional Hamming space. So D of phi is just the number of bits difference between embedded vectors. And our supervised learning setup, as I said, is like this. We have a point, sometimes we call it anchor point, and then we have some neighbors. So these blue dots are some neighbors. But then those neighbors have neighbors. Those friends have friends as well. So and those we call them minus. And as I said previously, these nodes or vertices are called plus. So the set of plus for any anchor, because for different anchors we have different sets. So when I say we have access to plus of x hat, it means that examples that are labeled as similar neighbors to x hat. And when I say x hat is we have access to minus x hat, it means that dissimilar examples, non-neighbors. And we call x hat, this is called anchor example. So the neighborhood structure is plus for any anchor point x hat and x hat minus. So it's neighborhood structure. That's the only terminology, if you like, to know what to do what we are going to create. So phi, as I said, phi, your embeddings, phi is parameterized as usual by deep neural networks. So we say that the phi of x and x prime is just 1/2 b minus phi of x transpose phi of x prime. And I noticed that there was just a mistake, a typo error in the article. It's transpose of phi that you write it as like this, like 1 by b vector. Phi b of x. And phi I of x is just the sign. Because remember, it's a hash. It's either 0 or 1. We are not doing quantum computing or quantum machine learning. So there is no complex plane. It's just either 0 or 1. There is nothing between. So it's a sign of Fi. Fi is activation produced by the feed-forward neural networks acting on X and your weights of neural networks. And so this is inside -1 and 1. Because we are not doing quantum computing. It's just traditional hashing. So I give you an example. Let's see what happens to the worst case. The worst case could be phi transpose of x, could be for x, could be maybe all of them are 1, all of them. So we have b bits, all of them are 1. And another example is that phi of x, but instead of x, we have x prime. And here, all of them are just -1. Of course, again, b times, because we have b bits. And if you just do the dot product of them, you will notice it becomes -b. So just substitute in your beautiful d phi of x and x prime, which is the distance between them, induced in distance. It means they are in the Hamming space. So it becomes 1/2 b minus, as I said, b minus b, b minus minus b, which is equal to b. So you may observe now that the phi of x and x prime is less than equal to b. And it is really interesting to work like this. So we have some text, because in original papers, they focused on images, but my concern is text. Because after all, this is the playlist for natural language processing. So what can we do for text? The idea is quite similar. Just substitute images with text. So all of these speech, text, images, all of these things are just the same thing. Is it text? Is it image? Is it speech? Is it DNA? All of them are just some language. You can see it as some language. And that's why nowadays people work on computer vision. You know that computer vision, they talk only about convolutional neural network. But nowadays, they have combined because convolutional neural network is very local, they use transformers, that is, first appears in BERT and those attention-based models in NLP. So they noticed that they can use it for computer vision as well. So nowadays, all of the algorithm in computer vision is just a mixture of transformers and convolutions. So you have a bit of a mixture of both. You have both local information and global information. And that's a great advantage that you will see in the next 10 years. Many of successes of the computer vision is just because you have combined the local and global ideas and informations. So we combine convolutional neural nets with transformers. Back to our idea that texts are plus neighborhoods, and we have text of negative neighborhoods for anchor point x. And for example, consider a text, it's dot. But because there are lots of neighbors, so we have some neighbors for the text, for the positive labels, if you like, and we have some labels for negative. And then you just give it to a deep neural networks, and your goal is to find this embedding phi, and what you get, as I said, is just a binary code. So what is interesting for me is that it has a distribution. It has a distribution. The other one is this. And what are these distributions? This is the distribution of d of phi of x and x hat, because it could be anything, but it is a conditional distribution. It is conditioned on x in plus neighborhood of x hat. And what is the other distribution? It is the distribution of x and x hat, but this time it is conditioned on x on negative labels. It is negative with the anchor point x hat. And we care about mutual information, and so we want to minimize neighborhood ambiguity. I'm sure you know all of these things that so let's call it D instead of little d, x hat and phi, and C for the label if it is in plus or it is in minus. So C is just the label. So this is according to simple rules. This is the amount that has been reduced from your entropy, information entropy. So, you know all of those things in entropy, and so mutual information is just how much it is reduced from your entropy. For example, if I know something about your output, what can you infer from the input? How much you could reduce your uncertainty of the input? And that's a beautiful concept. It can unify many of the concepts in machine learning, many of the concepts, if not almost all of them. So it is a very important and especially conditional mutual information. That's the future. You can develop lots of ideas and paradigms just based of conditional mutual information. And the beautiful thing is that you can combine the traditional classical computer science, which is all about combinatorial optimization, those STP relaxations, LP relaxations, with the machine learning, which is a little bit everything is continuous. Deep learning, everything is continuous. So it's a combination of discrete mathematics and continuous mathematics, and that's why it will shine. And it's the future of machine learning technology. And the goal is just to minimize the neighborhood ambiguity. So we like to satisfy the distance between x hat and a positive point to be less than d phi of x hat and xn. But unfortunately, these affinity matching methods, like the one like this, all of them are parametered. They need parameters. And the bad thing is not an ordinary parameter. Once you fix these threshold parameters, we call it threshold parameters, once you fix them, you do it for all of the anchors, and it's very bad. It's a bad rigidity. T2. So these are called thresholds. So you're dependent on these variables, these parameters, that once they are fixed, you cannot do anything because they are fixed for all of the anchor points. And the other approach is local ranking methods. They are much better, I like them more than affinity matching methods. They are less restricted because at least you have just one margin